Yeah, this works.
Yeah.
All right, finally get started. It's our morning session. So our first speaker today is Marcel Pawlowski from UC-HiPACC. He's going to talk about things related to planes and satellites or phase-space structures.
Thanks, Mike, and good morning. So since we moved this to a bit smaller scale than in the space, I first want to start with a little history lesson. The history of our knowledge of satellite galaxies around the Milky Way. In the last 100 years, we've discovered a ton of them, but most of those discoveries were made in the last maybe 15 years by SDSS and then DES survey and some other surveys as well. So our knowledge on those scales has kind of exploded. And that allowed us to also compare the observed system with cosmological simulations of Milky Way-like halos. So this is a movie from the Via Lactea simulation, but of course they are much more advanced simulations nowadays. But just in comparison, we see one of the small-scale problems that was discussed for a while, the missing satellites problem, meaning that there's much more substructure in dark matter than in observed galaxies. Then looking at those scales, you also find a number of other small-scale problems like Mike's working on the too big to fail problem or the Caucus problem. Now, all these problems have suggested solutions, and I would say more than one suggested solution. So you could say baryons can solve many of those. Feedback effects can change the potential of a dark matter halo. They can cause some sub-halos to remain dark. So solving those problems isn't really that difficult. You can also go to other models. You can go to warm dark matter to get rid of some of the substructure. You can do self-interacting dark matter. Some people would say you have to go to something completely different, like modified gravity, MOND, or something like that. But all those tests essentially rely on the internal properties of those galaxies. So I would like to argue that we can use those systems in a more robust way to test the underlying cosmology by looking at the phase-space distribution of those satellites and the observed satellite galaxies. And if you look at the phase-space distribution of the Milky Way satellite galaxies, well, let's first just look at the spatial distribution. You find that they are distributed in a very flattened structure. So you have the Milky Way disk in the center, and then these are all the satellite objects. The yellow ones are the confirmed, the green ones are candidates. And you see an edge-on view of this distribution here. Interestingly, also young halo globular clusters, which are thought to have been accreted by satellite galaxies, follow the same distribution, also in a flattened polar structure, so perpendicular to the Milky Way. And also, there's an overdensity of streams which aligns with this orientation. So there seems to be really a coherence in motion as well, and that's confirmed if you look at proper motion measurements of satellite galaxies. So we rotate this view around by 90 degrees, and now we see these arrows are the proper motion measurements for those 11 satellite galaxies for which we have them. So that's the 11 classical satellites, and we see that most of them are orbiting in the same direction, and in fact they are orbiting within this plane mostly. A similar structure was, well, the probability you can determine the statistical significance of this, assuming an isotropic distribution. You find it's about 4 sigma if you just look at the 11 classical satellites. Then if you look at the SDSS discoveries, I did this exercise of mock observing model distributions with the SDSS survey footprint, and you see that they actually add information to that, even though their distribution is biased by the footprint. So it's a highly significant structure. If we then go to our neighbor galaxy Andromeda, you see a similar plane. Rodrigo Ibata and collaborators found this. It's a subset of 15 out of 27 satellite galaxies discovered in the Panda survey. It's kind of seen edge on from our position. And if you look at the line of sight velocities, you color coded, you see that the upper ones are receding, the lower ones are approaching relative to Andromeda. So this also seems to be a rotating structure. And again, it's highly significant. So, whoops. We can look at the whole local group now and look at the orientation of those planes. So we have 2 planes, both are kind of in north-south direction. They are somewhat pointing towards each other, especially the Andromeda plane, and then both have the same rotational sense in this direction. So this appears odd because we've seen this dark matter movie and everything seems to be flying around in all kinds of directions. So what's the likelihood to find such a structure in lambda CDM? So we compare what we see with what we simulate. In this case, for the Elbow simulations. So down here, we have the root mean square height of the plane, so the thickness. And this is the radial extent. So this is only looking at the positions. What you see is this is the observed point. Everything to the left and upwards is more extreme than this. So we don't have any data points there. These are the simulated data points. Black are for paired halos, red are for isolated halos, and the green is just a randomized distribution if the halos wouldn't have any phase space correlation at all. So we see that if you compare the green and the points, there's a little bit of correlation, so they tend to be a bit lower, they tend to be a bit more to the left, so they tend to have satellite distributions which are a bit more narrow than isotropic, but the effect isn't very strong. And especially, well, to find something in the acceptable range as extreme or more extreme as the observed structure is about a 1% thing, if you only look at the positions. If you now also look at the correlation of those orbits, so down here, this is still the root mean square height. This is the concentration of orbits. So down here, everything is moving in the same direction very nicely. And up here, everything is moving in all kinds of directions. And the observed data point is again here. So everything more extreme would be in this corner and all the simulations on the opposite side. Especially, we see that, again, the concentration of these orbits, the alignment of these orbits is a bit more than in the isotropic case, but not much. So this reduces the chance to find the structure as observed to about 0.1%. You can also look at this in the axis ratio for a number of satellite galaxies. So you take the most massive satellite galaxies, you measure the axis ratio of this distribution. For the Milky Way, the observed classical satellites sit here. If you now add some of the other ones, this becomes a bit wider, but not much. But in simulations, you see that this becomes a lot wider as you add more satellite galaxies. So this is not just a low number, satellite number effect. And interestingly, these are hydro simulations, so they follow the same kind of trend as the dark matter only simulations. You can do the same exercise for Andromeda, of course, and that gives you a similar number, about 0.1% to recover the structure. And so that means you have two of those systems in the local group. Both are very unlikely, so the local group as such is even more unlikely, of course. But this is just the local group. You can go to other systems, and this is work led by Oliver Müller, a PhD student in Switzerland, who's doing really good work on this, on looking at satellite galaxies in the Centaurus group. And he found that there's a similar satellite galaxy plane, which also has correlated kinematics. So there are kinematics for 16 of those satellite galaxies, and 14 of those have a correlated sense of rotation, which aligns with the most narrow distribution of those positions. So you can do the same exercise again, and you see that this is about a 0.1% effect in lambda CDM. So somehow every system you look at, you find about the same unlikeliness. So something is going on there. I would argue this is a strong problem for our understanding of the simulations or the model itself, because these are relatively robust tests, as I said. It doesn't really depend on the internal baryonic physics going on in the satellite galaxies, where they are and in which direction they move. However, this is a highly controversial topic, so I argue this is a problem. Other people argue this is not a problem. Then some other people agree with me. So there's been a lot of debate on this issue, and I wouldn't say there's a consensus yet. But I think this was highly important, because in this debate we advance our arguments, we advance our analysis, and so we can learn something about the universe. So one of the reasons why, well, what are the reasons why we have this controversy? I think a lot of that is because different studies don't really agree on the methods, or the data they use, or the sample sizes they use. So there's certainly some kind of bias in the literature to either find an agreement or a disagreement, depending on what you assume. For example, if you look at satellite galaxies within a small volume, and then just measure the absolute height of a satellite distribution, you bias yourself to a more narrow distribution, of course, than if you look at a larger volume. So all these effects have to be considered. I don't want to go into the technical details because it can fill an hour, and nobody has time for that. So if you want to talk about that, chat with me later. What I want to mention is observational uncertainties, because that has not been considered so far. There have been arguments that the vast polar structure around the Milky Way is not dynamically stable, because you can just take the proper motion measurements, integrate them backwards, and see it is dispersing. Now, the problem with that is you can do a simple test. you set up a stable satellite galaxy plane and integrate it in a Milky Way potential. So this is the thickness of the plane. This is the time, 10 gigayears. It's perfectly stable. It's a spherical halo, so it should be stable. And yeah, the thickness doesn't really change. Now, what happens if you mock observe this with realistic proper motion uncertainties? So you get a distribution, and then you integrate it backwards. And now it just explodes. The proper motion uncertainties we have right now are so high that we cannot really deduce whether this structure is dynamically stable. Or we can say it's consistent with being stable. We cannot say it's unstable just because if we take the most likely proper motions, it doesn't work. But an argument why it might be a really correlated, coherent structure is if you look again at the history of our measurements of the orbital poles. So what's plotted here is the directions of angular momentum of the satellite galaxies. So if this is, for example, the Draco angular momentum direction right now, so the orbit is 90 degrees from that. And these are the uncertainties on that. And this circle here is the scatter of the 6 most clustered orbital poles. And then we have a normal vector to the plane of satellite galaxies. So you have a plane that has normal vector, and if the angular momenta align with that, the satellite moves within the plane. And 10 years, 11 years ago, this looked quite okay, but there's a lot of scatter. Now, in the last 10 years, this has improved. So we got more and more data. We got improved measurements. And just recently, there was another one improving more. And we see that this is really narrowing down on this region where we would expect it if the plane is rotationally supported. So I think this is a really strong argument. Interestingly, this is also close to the plane defined by the Magellan Extreme. So a lot of the satellite structure in the Milky Way seems to be orbiting in the same plane. And that's really unexpected from simulations. You can also look at distance uncertainties for the Milky Way satellite. That doesn't really make much of a difference because they are along the plane. But in Andromeda, this is really important if you want to compare simulations and observations. Why? Well, if you look at the edge-on plane we see in the sky in Andromeda satellite galaxies, and then you add distance uncertainties, this is what happens. The thickness doesn't really change. But if you would see a face-on plane and add uncertainties, it suddenly becomes thicker. So if you compare cosmological simulations, well, you look for satellite planes in cosmological simulations that are as correlated at the Andromeda satellite galaxy plane, and you do not consider the orientation or the uncertainties, then you overestimate the number of correlated structures because you do not add distance uncertainties. These distance uncertainties would always lead to a widening of the structure, so it reduces the probability to find such a structure in those observations. So I'm working on that right now. This is really preliminary. It looks like this reduces the probability by about a factor of 3. So this satellite plane problem, as I call it, is even worse. Okay, this is just one phase-based distribution. So in the last few minutes, let me talk about something else. It's also related, motivated by the local group. What we see here is the satellite distribution around Andromeda. You split it up into the hemisphere facing the Milky Way and facing away from the Milky Way, and you count the satellites. In pandas, you have 20 satellites facing the Milky Way and only 7 on the opposite side. This is called the lopsidedness of the Andromeda satellite system. It seems to be maybe connected to the satellite plane because the satellites on the plane are mostly on our sides, where the off-plane satellites are not as strongly lopsided. But we don't really know. And we only have this one system for now. So recently, Noam Libeskind did a study of looking for satellite distributions in SDSS. So you look at pairs of host galaxies, and then look at their distribution of satellites around them, and you stack that with with thousands of hosts and thousands of satellites, because each host only has 1 or 2 satellite galaxies. So if you do that, you can then look at this angular distribution of the satellite galaxies relative to the connecting line. So you measure this angle. So what does that look like in the observations? Let's have a look. So you do that in SDSS, as I said, and you measure this opening angle and everything which is in that compared to an isotropic random distribution. So this is the relative over or under abundance of correlated things. So we see that there is an excess of satellite galaxies in this direction. This is a red line, and the blue line is the opposite direction. So there's not really anything. But there's an excess of about 8% of satellites on this side between the host galaxies. Now, they only look at this in observations, so I was wondering maybe this is a problem for lambda CDM, or maybe not. So I looked at cosmological simulations. So this is what we see there. This is, well, the simulatic models applied to Millennium 1 and 2. The black one is the observed distribution. This is only a limit because you have fore and background contamination, so this true signal is probably higher. So everything above this is fine. And for Millennium 1, which is the most comparable in the number of satellites per host, you find a really good match. Also for Millennium 2, which kind of includes lower mass satellites than the observations, you find a strong signal in the direction between them and no signal in the opposite direction. So in that sense, lambda CDM seems to work on this particular set of phase-space distributions. It is a bit more complicated if you look at the details, you look at the 3D distribution. So again, now not in wedges, but in cones of satellites. And you see that this is the data, the solid line is the data for Millennium 1 in this direction. The dashed line is in the opposite direction. And then these thin lines here are if you include orphan galaxies. So these are satellite galaxies which have been, well, subhalos which have been disrupted in the simulation, but the semi-analytic model still follows them by, well, identifying their position with the most bound particle. And strangely, we see here a peak on the opposite side as well. So I don't really know what that means. It's one of the things we have to figure out now. It seems like these orphan galaxies are not really in a good match with the observations in comparison to the resolved satellite galaxies. But why they show a peak on this opposite side isn't really clear to me. Interestingly, this is not only the case in Millennium 1, but also in Millennium 2. This is a similar thing. And yes, as final comparison, I also looked at Erebus, which is even lower satellite numbers, and Illustrious. So the green one is Erebus. You see a similar trend. It seems like lower mass satellite galaxies show less of a lopsidedness. And Illustrious, the only hydro simulation which is big enough to try this comparison, unfortunately still isn't big enough. The statistics, there seems to be a signal, but if you look at the shaded region, which is the uncertainty, it is consistent with no signal at all within 2 sigma. So we need higher volume cosmological simulations to look at this, to have a sufficient number of pairs and satellite galaxies around that. So with that, I leave you with my conclusions, and thank you for your attention.
Since only a small fraction of the black matter subhalos are actually visible satellites, it may be that the baryonic processes are very important in helping these lanes to become very pronounced. The simulations that you have compared to, carefully done with aerodynamics, with high resolution, to really mimic the formation of satellites this small.
Well, the problem with that is you don't have a sufficient number of host galaxies with sufficient high resolution to do a good comparison. So I've shown this one plot with 4 lines. That's from Ahmed et al. They have kind of 4 Milky Way-like host galaxies. They don't seem to show a difference, but I think we really need to look at much larger statistical samples to do that. I mean, there is definitely one difference in the phase-space distribution if you look at hydro simulations, which is what Jay is working on, the disruption of satellite galaxies by the central galaxy that drives the whole distribution to larger radii on average, which then makes, if you find a narrow plane, makes that plane more statistically significant. Yes.
Final question.
You didn't mention the fact that we seem to lie in wall in the cosmic web. The most secure result, or certainly one of the most secure results of all the studies that people have done, is that the angular momentum vector for the larger galaxies that are in walls tends to lie in the wall. So the Milky Way, almost exactly perpendicular to the local wall, is actually quite normal. And the fact that most of the satellites appear to be in the wall, again, is just what one would expect. Andromeda is a slightly more complicated situation because there appear to be 2 walls that are sort of intersecting at Andromeda. But this large-scale structure of the cosmic web is a natural feature of lambda CDM simulations. I think we even understand where it's coming from. And isn't it possible that what you're seeing is just that effect?
Well, that's exactly the problem. This effect is already self-consistently included in the simulations I compared to.
Not. Absolutely not.
Well,
the simulations you're using are very low resolution and certainly don't include the ground.
Not all of them are low resolution. I mean, I compare to everything I can get my hands on.
But even if you did,
If you tell me which are the best ones and give me data access, I am happy to do that.
the only simulation that I'm aware of that actually has tried to simulate the satellites you're talking about self-consistently is the latte simulation, and it's only of one region.
Yeah.
So, as you said, it's difficult to find simulations that are adequate to compare. But when people say this is a big problem for Lambda CDM based on a poor comparison of simulations, I'm not extracting.
Oh, well, I didn't say it's necessarily a problem of the MSDM, but it might be a problem of the simulations. Yes, some of them, not all of them.
I think that's a great first stop. But thank Marcel and great to see you.
It was a good talk.